My name is Brian Scott. I'm the Sales and Marketing Manager with Rayco Systems. We're part of a three-company partnership with Idaho Steel and Kremco, and we're working with Boise State University to help us develop a better water removal system for one of our premier product lines, which is the Rayco Water Vac. We're working with them to develop a swirl plate that does a better job of removing water in a more cost-effective manner, and we anticipate incorporating this into some of our future products. Thank you.
Founded in 1975, Rayco Systems is a leading Idaho company that designs and manufactures innovative food production equipment. Since their humble beginnings, Rayco has become a premier supplier of the processed potato and French fry industry. A key line of their products includes equipment for removing surface liquids, including oil from fried products. Recovering these liquids for reuse can save food production companies tens of thousands of dollars, making Rayco machinery a very profitable addition to the food producers' processes. But the task of collection is easier said than done. For one, hundreds of gallons of liquid need to be recovered every hour, and they come in the form of really fine mists. For another, all of the equipment needs to be extremely clean for food safety reasons.
Mist and dust separation is a relatively mature science. The first separators started appearing around 1885. They work by swirling air with a mixture of either dust or mist particles in a vortex. Centrifugal force forces the particles outwards, and cleaner air can be drawn from the center of that vortex. Rayco's improved cyclone systems are larger and more complex than previous iterations. Swirl tubes, however, offer the promise of being a more compact and efficient solution. This project evaluates the ability of the swirl tube to replace existing cyclone systems.
Before taking on the design challenge, you have to understand the physics of what's going on inside the swirl tube. There are two different fluids interacting with each other, as well as all the internal surfaces of the device, and all of their interactions need to be taken into account. Now, there are established methods for determining the performance of conventional cyclones, and we really drew heavily on this theoretical base. But the device we're working on is a lot different from normal devices in the industry. So we had to do a lot of research into modifying the traditional approaches to carry over to this device. In the end, we were left with a lot of equations that give us a good estimate of what the performance is based on the swirl tube geometry.
Once we know how to predict the performance of a swirl tube, we can use that knowledge to design the optimum swirl tube. To do this, we decided on a number of factors in the geometry of the swirl tube to be optimized, like length, width, number of blades, etc. By plugging this model into a genetic optimization algorithm, we can quickly zero in on the geometry that our model says will be best at separating fluids. We can apply this process repeatedly to an array of criteria, finding the best geometry for a wide array of situations, such as different power or size requirements. Once we know what geometry works best for our model, we can test the results with a physical prototype.
In designing the prototype, we had to take into account food safety and cost. For food safety, the prototype had to be easily cleanable. We achieved this by making the tube assemblies modular and eliminating any hollow bodies. For cost, we had to look at the material we used to make the parts and the manufacturing techniques used to produce those parts. All metal parts were fabricated from stainless steel, since this is the industry standard for food processing equipment. Due to the complex geometries of the vein pack, 3D printing was used. With 3D printing, we were able to produce the parts quicker at a much reduced cost in comparison to conventional machine shop fabrication. The innovative swirl tube design we're evaluating has a lot of uncharted territory, making testing an essential part of this project. In order to fully test this design, we fabricated prototypes in several variants and a test loop that allows us to feed the swirl tube with air and water to test its effectiveness. Results from our tests are then used to inform our models for predicting future swirl tube design.